Hello students, today we are going to start a new chapter of class 12 physics, that is electromagnetic induction. Electromagnetic induction. So what is electromagnetic induction? Now you see, in class 10 you have studied that a current carrying conductor, this is a conductor suppose, and current is being carried by this conductor, and current carrying conductor generates magnetic field around it. This was experimentally proved by the scientist Oersted. So what will be the direction of this magnetic field produced around it? That was given by the right hand thumb rule. So this is the conductor suppose, and this is the direction in which a current is flowing through it, and towards that if you point the thumb and hold it this way, then the direction in which these remaining fingers other than this thumb will work around this conductor, that will be the direction of the magnetic field. That means in this case this will be the direction of magnetic field, going this way and coming this way. So current carrying conductor is generating magnetic field. Now question arises that is the reverse case is possible. That means can a magnetic field generate electric current or not? So the reverse case is also possible. That was experimentally proved by Faraday and Henry. Okay. So they have performed an experiment that was like this. Suppose this is a coil, and both ends of the coil connected to galvanometer, and this is the initial position of this middle of the galvanometer. Now here is a bar magnet. So here is the north pole and here is the south pole. We know magnetic field lines emerge from north pole and merge at south pole. You know that. You have studied those things in class 10. Yes? So when you bring this magnet towards this coil, or instead of the magnet you can bring this coil towards the magnet also, or you can move both. So whatever you do, in that case this magnetic field lines will be changing through this coil, and due to this change in magnetic field, an EMF will be developed in this coil. EMF means electromotive force, which is nothing but potential difference, and due to that the current will flow through this coil, That current is called induced current, and that EMF is known as induced EMF, and this phenomenon is known as electromagnetic induction, and this experiment was done by Faraday and Henry. So what happens here? One more thing. Suppose when you brought this magnet very fast towards the coil, suppose deflection is shown in this direction. Then again if you move it away from this coil, then what will happen? It will show, this galvanometer will show deflection in other direction. That means in both cases the direction of current is opposite. So what will be the definition of electromagnetic induction? So we can define that the phenomenon of generating current or EMF, generating current and EMF in a circuit or coil due to the change in magnetic field. Due to change in magnetic field, because you see, when you move this, when you brought this magnet towards this coil, and if you move it away from the coil, then these lines of force are changing across this coil continuously. Okay, and because of that change, this EMF or EMF is developed, or this current is flowing in the coil, due to which this galvanometer is showing deflection. So hope it is clear. And so that means the variable magnetic field is responsible for this production of current or EMF, generation of EMF, generating EMF. So this phenomenon is known as electromagnetic induction. So we can write, let me clean this first. So we can write that the phenomenon of generating electric current and EMF in a circuit by changing magnetic field across it is called electromagnetic induction. It is called electromagnetic induction. So that is the definition of electromagnetic induction. And the EMF so produced, and the EMF so produced is called induced EMF. It's called induced EMF, and the current so produced is called induced current. The EMF so developed or produced, you can say whatever you want to say, so is called induced EMF, and the current so produced is called induced current. So this is the idea of electromagnetic induction. To better understand this, we must know the concept of magnetic flux. Let me explain that. What is magnetic flux? Magnetic flux. Suppose this is a magnet. This is a magnet, this is the north pole, and this is the south pole. And magnetic field lines outside the magnet emerge from north pole, merge at south pole. Right? So these are the suppose magnetic field lines. Now let us imagine a surface here. Let us imagine a surface. Then magnetic flux through this surface is the measure of the number of magnetic field lines passing through this surface normally. That means we will take the normal components only which are passing through this surface. So magnetic flux, we can write magnetic flux that is represented by phi through a surface in a magnetic field. In a magnetic field is the measure of the number of field lines passing through the surface normally. So passing through the surface normally. Now here you see one more thing. Mathematically, magnetic flux phi is given by dot product of magnetic field. B represents magnetic field and A represents area vector. Okay. Dot product of B vector and A vector. B is magnetic field. Magnetic field is a vector quantity. Vector quantity means those physical quantities which have both magnitude and direction as well. So those are vector quantities. You know that hope you have studied about vector in mathematics as well. So you see dot product of two vectors. Suppose this is a vector, one vector, this is A, this is another vector, suppose B, and angle between them is suppose theta. Then dot product of these two vectors, A dot B, is equal to magnitude of A. You can simply write the magnitude without giving the arrow, B cos theta. Theta is the angle between them. Now here you see, so this is the surface. If this is the surface and so its area, this surface is facing towards this side like this, then the area vector, direction of the area vector will be this, and the angle between the magnetic field lines passing through this surface, angle between the magnetic field lines and passing through this surface and the area vector between these two vectors is suppose theta, then magnetic flux will be given by B dot A, and according to this rule, that A dot B is given by AB cos theta. Dot product of two vectors, A dot B, A vector dot B vector is AB cos theta. So it will be B A cos theta. So I am not writing the arrow. That means here I am taking the magnitudes only value I am taking magnitude. Okay, not the direction. So theta is the angle between this magnetic field and the area vector. So now you see, this is the magnetic field, direction of magnetic field, and the surface is placed like this. Suppose this is the surface is placed parallel to the magnetic field. Then what will happen? Then its area vector will point in this way, point towards upward or downward, either upward or downward. In both cases, that area vector will be perpendicular to this magnetic field. That means theta will be 90, and cos 90 is 0. Then this phi will be 0 for theta is equal to 90. That means that the magnetic flux will be minimum, because you see this is the direction of magnetic field lines. Magnetic field lines are in this direction, and this is the surface, and area is this one. It is stretching upward or downward. Okay, then no magnetic field lines is passing normally towards through the surface. And when you place this surface in this magnetic field in this way, if you place this surface perpendicular to the magnetic field, then maximum field lines will pass through it normally. And the angle between this magnetic field lines, magnetic field lines and the area vector, they are parallel, so this angle will be 0, and theta will be 0, and cos theta is 1, so for theta equal to 0, this value of phi will be maximum. This one will be maximum. Magnetic flux will be maximum for theta is equal to 0. So now you see, this magnetic flux is a scalar quantity. This is a scalar quantity. So, and its SI unit is Weber, or you can say Tesla meter square. So let me write here. So magnetic flux is a scalar quantity. It is a scalar quantity. Its SI unit is Weber, or Tesla meter square. And remember one more thing. Suppose this is magnetic field B, and a body is placed in this magnetic field. This is a body, and these inward field lines are considered to be negative, and the outward field lines will be considered to be positive. Remember those things. Okay. So why magnetic flux? This point I have discussed. Why have I discussed this magnetic flux? Because you see, in electromagnetic induction, I have already told you that this induced EMF developed here due to the change in magnetic field, due to the change in magnetic field lines across this coil. Change in magnetic field, that means change in magnetic flux. That is nothing but change in magnetic flux. That EMF induced in this coil or circuit depends on the rate of change of magnetic flux. Okay. So we will discuss this again, but now let us discuss the Faraday's first law. So what is the Faraday's first law? So Faraday's first law says that when magnetic flux linked with a circuit or coil, an EMF is induced, and that lasts so long as this change continues. When you stop changing this change in magnetic flux through this coil, then this EMF or current through this circuit will be vanished. No more. Then there will be no longer current flowing through this circuit and no EMF as well. So that was the first law of Faraday's first law. Let me write down Faraday's first law. So Faraday's first law says that whenever an amount of magnetic flux linked with a circuit, and EMF is induced, which lasts as long as the change in flux linked with the circuit continues. Okay. So whenever an amount of magnetic flux linked with a circuit and EMF is induced, which lasts as long as the change in flux linked with the circuit continues, then only the current will flow through this circuit or EMF will be developed. Without change in flux, there will be no EMF, no current in the circuit. So hope you have understood. This is the first law of Faraday, given by Faraday. And what was the second law? Second law says Faraday's second law. Faraday's second law says that the induced EMF, is directly proportional to the rate of change of magnetic flux across the circuit. That means this EMF E depends. This is directly proportional to the rate of change of magnetic flux d phi by dt. That means rate of change of flux d phi by dt. Okay. If rate of change of increase, that means flux change. If the flux changes across a circuit at high rate, then EMF will be high. Remember that. So to make it equal, we need a constant. In this case, this constant is equal to 1, so we can write directly E is equal to d phi by dt. But there will be a minus sign, and the reason behind this minus sign, writing this minus sign, will be explained in Lenz's law. Okay. So when we will discuss Lenz's law, then I will explain why I have written this minus sign. Okay. So we will discuss it in the next video. Now remember one more thing. Suppose this is the coil. This is the coil, and here this is the magnet, not pole and south pole. This is the magnet. So in this coil, if there are n number of turns, then this EMF induced here, E, will be given by minus n d phi by dt. So this is the formula to calculate EMF. So hope you have understood. Now in the next video we will discuss Lenz's law. Okay.